Well, welcome to National Astronomy Day indoors for 20 minutes or so. I'm going to talk about the sun, and I actually have to get all the way back to the beginning. But this is the very end of it. Yeah, and I have to speak backwards too. All right, so who's my Louis Armstrong singer? You gotta have this play in your mind. I see skies of blue, clouds of white. You know, the colors of the rainbow is so pretty in the sky. Also, like the faces of the people going by. It is a wonderful world. And part of the wonder of the world is that rainbow. I'm going to talk about the rainbow quite a bit in the next 20 minutes because the rainbow is really, more than anything else, probably what allows us to understand stars. And more than that, allow us to understand most of the evolution. So look at that rainbow, and what colors do you see? Red. Okay, I'm going to say red, orange, yellow, green, and blue. Can you live with that? Yeah. And Newton, who was the first guy who did this with a prism and started doing science about it, added violet, which would be way down here. And he didn't like having just six colors in the rainbow. So he wanted a seventh. So he said indigo. No, nobody knows what color indigo is, right? But those are the colors of the rainbow. Famously, Roy G. Biv, red, orange, yellow, green, blue, indigo, and violet are the colors of the rainbow. Red is the longest wavelength, and blue is the shortest wavelength. So the rainbow is always like that, where the red is on the outside and the short wavelength is on the inside. Um, and are we looking at the sun right now? Sort of indirectly, right? I mean, we're getting the light of the sun. My first question is, what color is the sun? I find it a difficult question. For one thing, because I've been working with the Library Telescope Project with CAAS for the last several years, and the first thing we do when we get library telescopes is we tack a sticker on them that says, "Never look at the sun." So if you never look at the sun, how are you going to know what color it is, right? Well, Newton thought it was white because if you run the sun's light through the rainbow, it splits it into red, orange, yellow, and so on. And then if you run that light through another prism, you get back a little white light showing on a card or something. But is it white or is it a little orangish white or a reddish light white or a bluish white? It makes a lot of difference. So never look at the sun. I don't look at the sun. You're crazy if you look at the sun a lot. But suppose you do. I'm also rebellious. All right. Are we looking at the sun now? You bet we are. Why is that okay? Because it's filtered, right? We've got a lot of water vapor between us and the sun, a lot of atmosphere between us and the sun. By the way, I mean, during the eclipse stuff, people were telling all kinds of scare stories about the sun. There's nothing dangerous about the sun's light, except there's too much of it. That's all. That's why you can't look at it. Is that it's just too bright. It'll burn your retina out if you stare at the sun. So I'm going to modify that never look at the sun, never stare at the risen sun. That seems to me reasonable. And never even glance at the sun with unfiltered telescope or binoculars. That's the real rule that we really want to get into people's heads as astronomers. And again, but suppose you do, because why not? Let's see what's going to happen if you stare at the sun with a telescope. Well, this guy got a pig's eye at his local butcher shop, and he decided to hold it up to the focal point of his telescope. And after a few seconds, it started to make an awful smell, and smoke came out of it. And after a little longer, a big hole burned right in the retina. I have a eyepiece cap for one of my eyepieces on my telescope, that solar telescope out there. I use it as a birding scope too. And one day I left the eyepiece cap off the front, and the sun happened to come right through the field of view, it burned a hole in the eyepiece cap. Two holes, really, because there must have been a tree in the way. So it's bright, it's hot, it'll burn things. We all have looked at this. I'm not going to go over this in any detail, although I got a kick out of the eclipse stuff because people were paranoid about checking the number on their eclipse glasses. I tell you what, if I'm a creep and a crook and I want to make cheap eclipse glasses that are no damn good, the easiest thing for me to do is to print the right number on the cardboard, right? I mean, I, the way you check stuff is you hold it up to the sun, make sure there are no holes in it. You know, it's not really super, super dangerous. Um, I don't like this way of doing it. Pinholes is a good way of doing it, but that anytime you're screwing around with binoculars and sunlight, I just don't like it. And the same with the telescope. Even if you're looking through my telescope out there, glance at the front, make sure that filter's on it. Okay, you don't want to make a mistake. That should be fine too. I mean, I don't know if it could damage the camera a little bit, but those are pretty doggone good filters when they're filtering it for your eyes. I personally wouldn't worry. I'm a little more laid back than most people about these things. The sun is this source of a tremendous amount of electromagnetic radiation, and that's wonderful. It keeps us warm. Every minute, 638 million tons of hydrogen are turned into 679 million tons of helium. So we're missing 4 tons, right? 4 tons of matter turned into light and neutrinos. Lots of light, lots of neutrinos. What are neutrinos? Well, they're almost massless particles that travel either at the speed of light or very close to the speed of light, and they don't interact with anything. If you hold your pinky up toward the sun and cover the sun with your pinky, something like 40 billion neutrinos will pass through your pinky in a second. It's like a lot of neutrinos out there. They just don't interact. A light year of lead would only have a 50-50 chance of stopping a neutrino. I mean, these things just, and they're tremendously important because a lot of the energy of the sun, a lot of the matter really in the universe is in neutrinos. So some of the missing matter might be tied up in neutrinos. A lot of it might be. What do we know about the sun and the way it produces its light? Well, it turns out not very much. Just like with Earth, we cannot see Earth's core, right? I mean, it's very hard to know anything. You use seismology to figure out what's happening in Earth's core. And with the sun, you use helioseismology. So it's the same thing. You're looking at sunquakes and you're trying to figure out what's happening. But physics and astronomy can tell us that the core of the sun has to be about 15 million degrees Kelvin. Well, what's that mean? Kelvin is the scientific temperature scale. At 0 degrees Kelvin, what happens? Everything stops. Nothing moves. 0 degrees Kelvin. At 273 degrees Kelvin, water freezes. And at 373, water boils. So it's sort of like the centigrade scale, but shifted way down. So at any rate, 15 million degrees is pretty doggone hot. It has to be at least 10 million degrees for that fusion reaction to happen. It's 10 times as dense as lead. So these are protons basically smashed together, bouncing frantically against each other and sometimes fusing into helium. Outside that core, there's this radiative zone. Again, everything's smashed together so hard that the photons can't go anywhere. As soon as they start to go somewhere, they hit a proton. And then they turn around and go, then they hit another proton. And they're trapped in this core for something like 200,000 years. I've seen different estimates. One said 40,000, but okay, this is astronomy. These are good estimates in astronomy. Off by a factor of 5 isn't bad. In the radiative zone, the temperature gradually drops as the protons can expand a little bit. And finally, you get out to the convective zone where they're cool enough, they can start recombining with electrons and become hydrogen, become helium, and then you get convection, which is pumping heat out toward the surface. The only part of the sun we see is the photosphere. So that very, very external part that you may have looked through my solar telescope and already have seen. And we're going to talk a little bit about that. So it's 5,800 degrees Kelvin, the solar sphere, which is photosphere, which is, you know, pretty hot, but not super hot. It's got granulations. Note, it started out 10 times as dense as lead. Now at the photosphere, it's 1/10,000th as dense as the atmosphere on Earth. And this is very bright, so light can just barely escape it because everything's moving so fast, but it finally can escape and light can come toward us. And then outside the photosphere, there are these two other zones of the sun that we all enjoyed during the eclipse, the chromosphere, and during that part, the temperature of the sun drops from 5,800 degrees to 4,300, and then it goes back to up to 8,300. And that's very important in science because that drop in temperature and that increase in temperature allows us to take solar spectra, and we'll see an image of that in a minute. And the solar spectra allow us to determine exactly what elements are in the sun. It allows us to determine a lot of how the sun is moving in space. These solar spectra are incredibly important. And then out beyond the chromosphere is the corona. I don't think anybody understands the corona very well. It is just incredibly hot, 2 million degrees Kelvin again. And I'll explain a little bit of that, but not that much. The sun is very, has a lot of electromagnetism. So it's basically the electromagnetism which is creating these very hot parts of the corona. But I don't think people really understand it totally yet. Cecilia Payne-Gaspachin. She was Cecilia Payne at Harvard in 1925 when she wrote her thesis. And she was, I think, one of the first women to study astronomy in England or America, faced a lot of resistance. And her thesis, one of the Harvard dons said, was the best thesis ever. Because what she realized, until she came along, people thought the sun was made of just ordinary matter. So you take a really big Earth, and gravity will make it super hot, and stuff will burn. And that's what they thought the sun was doing. Just the stuff all around us is burning. And gravitational contraction heats it up. But then they started to do the math, and it wouldn't work. The sun would have been all died out after 25 million years or so. And they knew it had to last billions of years. And it was Cecilia Payne-Gaspachin who first looked at the sun's spectrum. So as it moved from that 5,800 degree surface through the corona and went down to 4,300 and then back up to 8,300 or so, the gases in the atmosphere of the sun will absorb light. And the bands of light that they absorb tell you what those gases are. And so you can put things in Bunsen burners on Earth and you can look at the spectra they produce at those temperatures. And that's basically what she did. She figured out that almost all of these spectral lines are created by hydrogen, which means that by molecules, 90+% of the sun is hydrogen. Now, it's not ordinary stuff at all. By weight, it's about 73, 74% of the sun is hydrogen. So she changed the history of astronomy in that sense. We now know what stars are made of, and we could then begin to figure out how they burned. And if you look at, by the way, we're back to the rainbow, right? I told you the rainbow was going to be important. And this rainbow is telling you exactly what elements are in the sun. All of them, all of the elements in the sun are going to show up with these lines. And not only that, but if a star, not the sun, if a star is moving toward us, I might get this backwards, Shawn, correct me, but those bands should be blue shifted. And if it's moving away from us, those bands would be red shifted. So it tells you the relative motion of the sun to us. And again, if two stars are rotating around each other, the red shifting and blue shifting will tell you how fast they're rotating around each other. And then you can determine how massive they are. And you can start to, figure out everything about how the universe works, really. And it's from solar spectra for the most part. Not all of it, but a lot of it. This is a black body spectrum of the sun. And what's that? Yellow line, I guess I'd call that yellow, is the ideal black body that's at 5,900 degrees. So that's what it should look like. And measurements of the actual spectrum at the top of the atmosphere show it very close to that. So the sun is very close to an ideal black body. And then as things go through the atmosphere, various wavelengths of light get absorbed by things in the atmosphere. And we get the actual spectrum of the sun. But we're back to our rainbow again, aren't we? And if we look at that, what color is the sun? What wavelength is its maximum radiation going out at? Pardon me? Okay, so this is the actual spectrum we're looking at. Yellow is below green, isn't it? I'm saying the sun is green or slightly blue-green. I don't know. I make this up. I kind of like it. If you look through my solar telescope, and that's a white light filter, what color is the sun in that white light filter? Kind of, one of those two colors, right? Yellow, orange. But what color is the sky? Why is the sky blue? The sky is blue because blue light gets refracted by the atmosphere. So blue light is subtracted from the sun as it's passing into our atmosphere. And you get to even hotter wavelengths and none of it gets through. So UV light doesn't reach Earth at all. It's too refracted. But blue light is refracted just enough so it's scattered all around. Now, plenty of blue light still comes through from the sun. But suppose you mix up a little blue and yellow. What color do you get? Green. I'm sticking with green for my sun. And I'm not going to look at it, so I'll never know. All right. This is a famous chart that astronomers use called the Hertzsprung-Russell diagram. And once again, we're back to the rainbow, aren't we? Except it's got a difference. It's got red, orange, yellow, white. That's where green would be, right? White, blue, and violet. So the astronomers, observational astronomers, like to call that light white, which is in fact what we see. I mean, if we mix all the colors of the rainbow together, our brain interprets it as white. That doesn't necessarily, in my mind, make it white light. The maximum wavelength of that light isn't white. It's probably green. But our brain has short wavelength, medium wavelength, and a long wavelength receptors. And we put together a vision of the universe from the way those are triggered. At any rate, our sun is right in here. And in this one, it's in the yellow zone. And this, by the way, this diagram, we could spend hours on it. But this is called the main sequence. And most stars are on the main sequence for billions of years. And then for really short periods of time, like hundreds of millions of years, they go off the main sequence and become these other stars. A lot of the ones we'll see at night, though, are these giants, red giants, various giant stars. Why? Because they're giant and they're bright and easy for us to see. This is pretty much what you saw out there and what you'll see again when we go outside. You see a lot of solar uh, uh, sunspots, and you also see that the center of the sun is much brighter than the edge of the sun. And that's because we're basically seeing through the edge of the sun a little bit. So we're seeing only the cooler sunlight. When we're looking straight on, we're seeing deeper into the sun and we're getting the hotter sunlight. So, you're kind of looking through the edge, and that's why it's a little darker on the edge. And this is basically what we saw in the hydrogen alpha filter view as well. Solar flares, and if you're lucky, you get to see these black lines and white lines. The black lines would basically be the solar storms coming up and arcing over and going back to the sun. And the reason they're black is because they're cooler. They've launched off the surface of the sun. And those bright yellow ones are obviously hotter, but I'm not sure why. Each of these little granules is about the size of the state of Arkansas. And here's the sun, the granulation of the sun. It's like a boiling pot of honey because the hot air comes up and it's bright yellow as it comes up. And as it's going back down, it's a little darker in color. So it's not irradiating, giving off as bright a light. Yeah, this is an image from the sun. Oh, they have wonderful stuff. Soho gives you current images of the sun daily, and you can watch all this stuff live if you want to. Yeah. Right. This is 10 days of following these sunspots. So you're watching these sunspots evolve over 10 days. You'll see the limb of the sun come over after a while. Look at how they get bigger and bigger, and they will stay on the sun as the sun goes all the way around. And, it takes the sun at its equator takes 25.34 days to rotate, and the sun at its poles takes closer to 35 days to rotate. Well, what does that mean for us? If the equator is rotating faster than the poles, it means things get tangled up, doesn't it? Eventually, those gases start swirling, kind of like a tornado. And that's sort of what sunspots are. They're these little tornadoes where electromagnetism has been wound up by that differential rotation of the sun, and it bursts out. So you've got the cooler area, which is the umbra, and the hotter area, which is around it. And these look like magnetic filings, don't they? And it's because it is magnetic. The sun is a ball of proton plasma, and it's moving, so it's getting stirred up. And when you have moving electrical charges, you get a magnetic field. And these magnetic fields over an 11-year cycle, really a 22-year cycle, get more and more tangled up. This is the cycle of sunspot observations as far back, I think, as we've got them, which is the longest scientific record there is, truly scientific record there is. And you can see every 11 years, a new cycle begins. We're right just past the peak of the current solar cycle, which has been wonderful, right? How many of you saw the aurora? Yeah, you don't see that every solar cycle. I mean, this is really, really rare. And again, here's a little more detail. This shows you what percentage of the sun is covered by sunspots. You can see 1960, there were a lot of sunspots. And when there are a lot of sunspots, that means the sun is a little hotter than normal. And when the sun has very few sunspots, it's a little colder than normal. I'm going to go back one slide just to show you. Here there were almost no sunspots for 50, 75 years. And that was the Little Ice Age. It was so cold that, everything was freezing. And then you have these modern maximum. We've been in a period where the sun's been pretty warm and everything's been pretty nice. It's like, okay. And you can see on both of these charts, here's where they're located in the sun. And they start off far from the equator and they gradually move toward the equator. And I'm going to show you in the next slide where we currently are in our current cycle. We've just probably passed the peak. You can see that the prediction was for a much tamer solar cycle. We've had a much better solar cycle than they were predicting, which is why we've had aurora everywhere. Things aren't necessarily over yet either. You looked in the hydrogen alpha filter and you were seeing flares on the limb of the sun. And that's what you were seeing there. Those beautiful flares coming off in here as well. And that's probably several hours, I think, of photos of the sun. So these things are active real-time events and tremendously energetic. 10 million, 20 million degrees, those flares are sending electromagnetic radiation off. It's X-rays all the way through the whole spectrum. And all of that comes at light speed, so it gets to Earth pretty fast. We will then get coronal mass ejections, which are even more fun. Yes, sure. Coronal mass ejections would be larger, obviously, and now I'm dropping the term, but when stars blow up, what's that shot? Supernova, type 1, type 2 supernova. Supernovas are bigger. So there are a lot of things, but those are very powerful events on stars. And in our solar system, there's some of the most powerful events. The more powerful event are the coronal mass ejections. And those are the really fun things for us because those are the things that produce this pretty aurora that we saw. Here's a coronal mass ejection, boom. And it happens fast. I mean, that's not real time, but the sun takes, 25 days to go around. That's probably hours, that big coronal mass ejection. Sending off, and here's the size of the Earth by comparison, and it's sending off matter. It's sending off protons. It's not just sending off light. And that matter, and they're beautiful, twisty things. And that matter starts coming toward us at up several million miles an hour. So the solar flare gets to us in 7-8 minutes. Coronal mass ejections take 2 or 3 days. And that's how they can predict aurora a little bit better. But boy, they're powerful things. In 1989, Canada's entire electric grid went down. And in February of 2022, 40 Starlink satellites were vaporized. In 1972, one was so powerful that it set off, the magnetic influence sea mines. And the best one of all is the Great Carrington event of September 1st, 1859. This guy Carrington was looking at the sun, just like you were doing with my solar telescope, and he saw this thing unfold in real time. He saw this sunspot getting bigger and bigger and huge. And we had 1 or 2 this cycle that were about the size of the Carrington event. And sure enough, a couple of days later, everything fell apart. They didn't have the satellites we had, but people who ran telegraph operators were knocked off their chairs by the power of that sunstorm. It was just phenomenal. And they are still like that. I mean, we have to turn satellites around to protect them in case of solar coronal mass ejections. So we're just at the peak of our solar cycle. Carrington event happened just after the peak of that solar cycle. We could still get one. We might get lucky. We might blow all the satellites out of the sky. Anything can happen. All right, thank you. And now take any questions. I'm not swearing I can answer them. Yes, yes, yeah. Yeah, it always stays a little further to the south. Yeah, but I grew up in northern Wisconsin. It got pretty doggone hot up there too. Yeah, I think that's. I think it's the. I think it's mostly the humidity that is bothering us with the sun. But yeah, yeah, yeah. The humidity is something else. Oh, did it? Well, yeah. Well, we don't do much solar astronomy in the midday in the middle of the summer. Yeah. Yeah. Well, I guess it's Sean's right. It's enough to make a difference. Uh, well, it was pretty hot out there doing the solar astronomy too. But I invite you all to come out and join us again for solar astronomy. We'll be doing that until dinner, I guess. Is that right, Sean? And you have another speaker, I believe.
Alrighty. Thanks everybody for coming out and celebrating National Astronomy Day with us at CAAS. We're going to have a quick presentation about what's up tonight with Bruce McMath and Daryl Heath. And I wanted to briefly talk about that tonight the waxing crescent moon will shine brightly in the western sky. The reddish dot of Mars will glow below it just after dusk. Uh, if you have binoculars, you should be able to see the delicate scattering of stars in the Beehive cluster, also known as M44. It'll be just southeast of Mars. Then we'll witness the moon's dark edge pass over a star called Acellus Borealis, the northern donkey, in the constellation Cancer, a celestial event known as a lunar occultation. With binoculars or a telescope, you'll easily see that the moon will slowly cover the star. And throughout the night, we'll have volunteers set up to see the moon, Jupiter star clusters, and other deep sky objects. I want to take a moment to thank all of our volunteers again. Stephen Meeks, thank you for bringing your model rocket. We also had Katie Harder and Daryl Heath, Carl Frialdenhoven, Bill and Kay Sanders, Catherine Norwood, Jeff Hoeper, and Don Wynn. and Darcy Howard. All right, and before I turn this over, I briefly wanted to show the occultation that we'll see tonight. Let me drag this over. One moment. All right, so this is the constellation Cancer, and this star right here is the Celis Borealis. Here's Mars, and there's the Beehive cluster, also known as M44 from the Messier catalog. So what we're going to see tonight is, from our perspective, the moon will eclipse Acellus Borealis. But all of these will be in a tight cluster. It'll be easy to find Mars and M44 in the constellation Cancer because all you need to do is find the moon. And I've got a video to show us what this event's going to look like. Let me drag it over. Green. So this was made at the starting in the day and then ends with the occultation about 12:40 a.m. So this bright star right there, that's the sun. And then right here, this was just whenever the moon was starting to rise. There's Cancer. So I'm going to start this and we'll see. So there's Acellus Borealis. So what we'll see is the moon will begin eclipsing it at around, I think 9, a little after 9. You can see M44 right there, and there's Mars. And so the moon is eclipsing it, and then around 12:40, will the occultation will be over, and Acellus Borealis will be visible again. Occultations have been historically an important measurement technique to determine the times of orbits for nearby objects. So you can determine the speed that the moon is going if you know the diameter of it by timing the eclipsing event. So I'm going to turn this over to Bruce McMath, and he's going to tell us some more about what's up tonight.
I asked Rocky. He usually does our What's Up Tonight program, and he couldn't make it tonight. So I asked him to make a slideshow up for us, and he did. I should have just had Shawn do it. I, I, my role here is the chair of this event. That's somebody's got to do it, you know. And I've been up here twice today because I got up here with everything I needed except the crock pots. I had to speed home and come back with the crock pots. All right. So Rocky made this, not me. So he gets the credit. Now, the first thing, a little bit about the time of year and the sky that you have this time of year. As we go around the sun, the neighborhood we're in at night, or what we're seeing at night, changes. So in the summer, we have the summer Milky Way. And it won't be too much longer towards the end of this month. We'll start to see the summer Milky Way and the summer constellations coming up. But they'll be up this morning. I mean, late tonight, early in the morning now. But that'll start to become our sky And that lasts a long time. We won't get into why, but it goes on into the fall. In fact, we have the Dark Sky Festival. You heard us talking about the Dark Sky Festival. We usually have that in September, October, and we have it then in part because there's so few clouds that time of year. You got a better chance of it, and because the summer Milky Way is still up. But then we move into the winter Milky Way. The summer Milky Way, when we're looking at summer Milky Way, we're looking towards the center of the galaxy. And so it's brighter than the Milky Way itself is brighter than the winter Milky Way. But the objects in the winter Milky Way tend to be better and closer and brighter because we're sort of in that arm, the Orion arm of the galaxy. And so in the winter, we're looking in our neighborhood, whereas in the summer, we're looking way off towards the center of the galaxy. We can't see all the way to the center. We just see the arm that's inside. But this time of year, we're looking out of the Milky Way. So the Milky Way is a big disk, and we're going around the sun about halfway out. And so in the summer, we're looking towards the center. In the winter, we're looking out this way. But this time of year, we're looking like this, perpendicular to the plane of the galaxy. So what we see is entirely different stuff than in the winter and the summer Milky Way. In the winter and summer Milky Way, as we're looking through the Milky Way, there are a lot of open clusters, what we call open clusters. That's just balls of stars, collections, I should really say collections of stars. Stars are born in groups, and they stick together for a while, a couple of 100 million years before they scatter. And so you can see these clusters that are, a few 100 million years old typically of stars. And that's one of the fun things we like to look at. And then, but this time of year, you don't see, there's only one significant one, and he's referred to it, which is Messier, the so-called beehive cluster, Messier M44. Now, what we will have up is lots of galaxies. Okay. Summer, you're trying to look through our galaxy. You can't see very far because it's so thick. In the winter, we're looking out this way, and there's still a lot of stuff in the way, so you don't see a lot of galaxies. The galaxies are in the spring sky when you're looking like this. So all of a sudden you've got galaxies. And the other thing we have is globular clusters, although there's only really one good one that'll be up early this evening, M3. And globular clusters are balls. They're like, I liken them to popcorn Christmas tree ornaments. People used to make those. You'd pop popcorn and then you'd stick them all together in a ball with some kind of taffy kind of stuff, and hang it on a tree. Well, that's what they look like. It's a real dense ball of stars, and those clusters are about as old as the galaxy itself. They're really old structures, and they hover outside the galaxy like bees around a beehive that's been disturbed. They're around the galaxy. So this time of year, when you don't have anything else in the way, you're looking up and you can see these beehive clusters. Someone will put M3 in one of the telescopes. In the northern hemisphere, the better one is a little bit better, is M13, but it won't be up before everybody goes home tonight. So you'll get the idea with M3. So you'll get one open cluster, M44. We'll probably put it in those big binoculars out there that you see. And then this big Newtonian here on the deck, we'll get M3 in that, and maybe some other people will have M3 in theirs. And then we will have some people showing you some galaxies. It's the brightest and best galaxies are not up right now after I've told you that this is the season for galaxies. But Andromeda and M33, I don't think M33 is up either, is it, Shawn? Yeah, probably the two brightest in the sky that you actually naked eye under a dark sky, you can see. Andromeda is 2.2 million years away. It's our nearest major galactic neighbor, 2.2 million years away, but you can see it with a naked eye under a dark sky. If you go to the festival, you'll be able to see that. Then one more thing before I start flipping through this, you hear about these M objects or Messier objects. So that's a catalog or a list of objects that Charles Messier, 17th century, 18th century French astronomer who was fascinated with comets. Back in those days, comets were a hot item and a big curiosity. And so he was a comet hunter, and he would run across these fuzzy little objects, which these galaxies you may see tonight are going to be fuzzy little objects. You won't be able to see much detail. You'll just have to marvel that you can see it at all when it's millions of light years away. And with the moon up, doesn't help. So he would run across these fuzzy objects in his little primitive telescope, and then he would have to watch them to see if they moved, because he couldn't tell the difference between a fuzzy object and a comet, and that's what he wanted to do, is catalog and follow comets. So he hit upon the idea that rather than having to constantly revisit these things and figure out what they were, he would make a catalog of them. So he made a catalog of a little over 100 of the best and brightest deep sky objects. And by deep sky, we mean anything outside the solar system. Okay? And so there are a lot of globular clusters and open clusters and galaxies in his list. And so when you see that, that's what that refers to. So one of the things that's up, and I don't know that you're going to be able to appreciate it tonight, is Macarian's chain. It's just a group of string of little galaxies as shown in this picture. And if you have a dark night and you've got a good telescope, you can come up here and walk your way through, and they look somewhat like that. You can get, maybe, depends on the telescope, 3 or 4 of them in at once. A nice pair of binoculars, you might be able to pick a bunch of them up in a single view. I don't think you're going to be seeing those tonight. I don't know why Rocky put that here, except it looks good. All right, so now this isn't working. Let's see. How do I advance? What do I click? Because the arrow keys isn't doing it. Okay, now they'll work. All right. So when the moon's up, you got to look at the moon, because the moon hogs the sky. Even a quarter moon is really bright. So some of the fun things to look at on the moon that you should try to focus on tonight when you're looking at these telescopes, and then early in the night, early this evening, everybody's going to be looking at the moon. Every telescope out there is going to be looking at the moon probably. And then later we'll go to, some people will go to Jupiter, and maybe we'll get some people to look at Mars. Mars doesn't show a lot, but sometimes you can make out some caps, polar caps and so forth. But the moon will be the beginning of the deal. And you've got basically 2 major features that make up the face of the moon: the highlands, which are all these pock-marked craters, and the seas, so-called seas, the dark areas. Those are areas where lava flowed some 3.8 billion years ago. I'm going from memory now. We had these large lava flows and filled in some of the really big early craters. They just had low floors, and they filled those in. That's what those really are, is low areas, mostly from big, huge craters. And most everything you see on the moon is about 3.5 billion years old or older. There's no wind, no water, there's no tectonic plates, so there's no etch-a-sketch. There's nothing to erase it, unlike the Earth. So pretty much everything you see is really, really old. The younger things, every once in a while you'll see something that's got white rays coming out of it, and that's something that's not quite so old, and that's where something is hit and blown a bunch of stuff out, and you get just under the surface, and that has not been weathered by the solar wind and is lighter in color, and you can follow the little rays out with little pock marks where the stuff comes down and hits again. Whether that's best seen during full moon. So Mare Fecundus, Mare Tranquillus, okay, The A there, that's Apollo 11. That's where Apollo 11 landed. And you remember they hollered back that they had landed at Tranquilus Base. So that's where that was. They were real chickens at the time, and so they wanted to come in here and land where it was all this clear and not get into this stuff here. Then later, they get brave and they see where they start putting down in 16 and 17 into this rockier. Apollo 16 and 17 are on here. So you'll be able to see, if you'll find Mare Tranquillus, look one end where you've got this conspicuous crater, and then you'll be able to over here and see there, and then Apollo 11 down here, and this is going to be hard for you to spot without a map, M16. So, and then these are just some large craters here. They'll just be, and when you look at the moon, look at all of it, but this is where you really want to focus, right across where that's sunrise on the moon is what that is. And so when you look along there, you'll see illuminated peaks on one side, and you'll see shadows on the other side. So you get a three-dimensional feel for the topography. All right, so that's the moon. Now, constellations. So Orion is just sneaking off the winter Milky Way. I mean, the most popular winter constellation is in the process of sinking out there right now. We maybe just catch a glimpse of it as it goes down for the season. Gemini, the twins. Cancer, he's already mentioned Cancer up here at the top. Those are some of the principal constellations. Now, constellations are just patterns of stars. There's no physical or scientific connection to them at all. But the classics, the ancients, put their folklore, their culture, they hung their culture on the patterns they saw in the stars. And so these star patterns were important to our ancestors. And they had all these stories of the gods, their heroes, and the villains. And we inherited those. And so we still use them. And in fact, the sky, by scientists, astronomers, divide the sky up by constellations. It turns out that some of these constellations that we would recognize today, they're all very old. We don't really know how old they are, but it now appears that some of these cave art, 30,000-year-old cave art, that the figures, the animals and the people are not necessarily just animals and figures. They're constellations that our Cro-Magnon ancestors were following, including one that's quite recognizable to us today, which is Taurus the Bull, which this depicts. And I just thought I'd throw that in there. It's not up tonight, but that's fun. That's part of the winter sky, the Pleiades and Taurus the Bull and Orion. So, but this is the spring diamond, and when we say something like this, those are asterisms. The spring diamond is an asterism, and it's just a pattern of stars that people recognize, and they're useful when you're trying to learn the sky or find your way around the sky, because if you know these asterisms, it helps you find where sort the sky out into its various constellations. And here's an example: the Big Dipper will be up tonight in the north, and if you take the handle of the Big Dipper and you follow it, it's got an arc in it. You see it has an arc in it, and so you arc over to Arcturus, and then you speed to Spica, and then you go over here to Denobula, which is the tail star in Leo. The line in Leo is real easy to spot, and then up to Coriolis, at the top up there, a little second magnitude star, all this surrounding Coma Berenices, you've got the spring diamond, and that helps you find these constellations of Boötes, and then right next to it is Corona Borealis, and then Leo and Leo Minor, and you see how this happens. You just star hop, and all you need is a little sky map. Did any of you print out a monthly sky map like I suggested? Alan did. Yeah. Yeah. Oh, did you? Oh, no. All right. Well, you print out a monthly sky map for the month you're in, and then you just go out in a reasonably dark spot. You don't have to be pitch dark, and look north, and you can, knowing that you're 35 degrees north of the equator, you look north and you put your fist out. That's 10 degrees. 1, 2, 3.5, and you should find Polaris, the North Star. Okay, and then you can double check that, because if you can see anything in the sky, you can see Ursa Major, and the pointer stars. These two stars right here point to Polaris, which is off the chart here, and 5 times their length. 5 times their length is Polaris. So you can confirm, now I know I got Polaris, and I know I've got Ursa Major. Then you arc to Arcturus if it's a spring sky, and speed to Spica, and all of a sudden all this starts falling together. All right, so that's your little sky lesson. This is just showing that. All right, let's see now. What do we want to do? Talk about Boötes. There's oh yeah, T Corona Borealis. If Shawn will let me, he's going to run the 6-inch tonight. If he will let me later, after we've done the moon and got the occultation, we'll try to find T Corona Borealis. And T Corona Borealis is a nova, and all the amateurs are watching it close right now because it's supposed to blow up, okay, or get a lot brighter, not really blow up. And everybody is overdue. Everybody's following it. So I've got a little chart. We'll get it in there, and I hope I've got that chart. I hope I got here. Well, I'm pretty sure I did. And everybody can do what amateur astronomers have been doing since 1609, which is look at a variable star and estimate its magnitude and record it. And of course, these days, since about 1879, I guess it is, there's an organization that you could turn, as it was Harvard University at the time, you turn your observations in. Now, these days, it's the American Association of Variable Star Observers. So for a minute, you can be a variable star observer, hopefully tonight, and make your own estimate, and we'll write it down, and we'll see how close we all are to one another in our guesses about how bright it is. But basically, the chart shows other stars of known magnitude on it. And what you do is you say, okay, you take, it's brighter than that one, it's brighter than that one, it's dimmer than this one, and you bracket it, see, that way. So it was brighter than this star, it's dimmer than that star. Well, it's not halfway, it's a little closer than you estimate. You get it down to a tenth of a magnitude, and you record that. And believe it or not, enough people do that, you can turn that into meaningful scientific data. And it has, I mean, the Association of Variable Star Observers has got several million observations in its records now, going back to 1579. So that might be fun to do that, and we'll see if it's excited or if it's still about 10th magnitude. All right. I told you about the galaxies, the Virgo cluster, and the Virgo constellation, just aft of the tail of Leo the Lion. I don't know if anybody will bother to put a telescope on it, particularly with the moon out. They're going to be pretty disappointing. There is Lilo, and you can see it's got more, almost all, those are all galaxies underneath there. Now, Leo is a zodiacal constellation, and you know, my dad used to ask me about my astrology hobby. There was a time when when priests and astronomers were the same thing, and they just everybody knew that the heavens were full of information, because after all, it could tell you when to plant, when to harvest, when to migrate. It could tell you the season, and like clockwork, it's entirely dependable. The time of day and so forth and so on, the time of year, and so it had to be full of information. Well, everything up there moved with absolute rigidity. It just went around like a clock as you went through the year and through the night, year after year, unchanged, and except the planets. And the planets wandered around. And the planets wander around the ecliptic. And the ecliptic is if you just take the sun and you take the Mercury and Venus and Earth and so forth, it all goes out, and it's more or less a flat plane like that. So that is when you look up at the ecliptic, that's what you're doing. You're looking out where things eclipse, where things are that eclipse to all these planets. Well, they were fascinated with them, and so they thought if Mars was in some constellation, that meant one thing, or if Jupiter was in a constellation. So those zodiacal constellations were really important to our ancient ancestors, and so we inherit it now, and you look and see what birthday you're in, and so forth. But that's what that is. And when we get out there, we'll see if I can show you, if I haven't waited too long, how to find the ecliptic when you go out to observe. So a triplet, I'm trying to talk somebody into putting this the Leo triplet in the scope. I think we could get all that in one field of view. We can get the right scope. Let's see here. I wish I remembered the story about coma bernasis. I think, isn't that the story that Rocky tells where what? Okay. No, go right ahead. So mad that he had the guards go in the temple, rounded up all the priests, brought them out in the courtyard. They thought that all executed right there on the spot. One of them, very smart, very wise, pointed to that little patch of sky and said, "Look, Ptolemy, it was the gods. They're the ones that stole your white hair to put it in the sky to commemorate your great victory." And either Ptolemy didn't know the sky very well, or else he was just that vain anyways, and so forth, and blind and thinker. So here, thousands of years later, all of our still in the sky. Which is all these stars here, all these stars there. Yeah, it's a fuzzy thing. Thank you. So let me see. I think we're about through here. One other thing I wanted to point out: these are the owl, another kind of object. Maybe somebody will get it in there tonight. M51, the Whirlpool galaxy. Oh, you're not looking at it. What? There it is. So take that away, and that's what the Milky Way largely looks like, this spiral affair. And maybe somebody would get the Owl Nebula in tonight. This is stars. Stars don't live forever, and when they when they run out of fuel, depending on how big they are, uh, how big they are to start with, different kinds of things happen. If they're really big, they become supernovas. But more commonly, you have what we call a planetary nebula effect, where the star just it gets big and it just swells up, and then it starts throwing its outer layers off. And so down deep in this is a star, and it's just been throwing itself off over a period of time. And yeah, now you won't see color in a telescope. It's going to be black and white. And the reason for that is because when you're looking at, and that reminds me, when you're looking at a telescope at a particularly dim object, or even a not so dim object, to tell you the truth, unless it's the moon or Jupiter, something really pretty bright like that, you want to use averted vision. You can look at it if you want, but you're going to see it better if you just look off to the side. And the reason for that is that when you're looking at these dim objects in the telescope, you're using your rods, the rods in your eyes, not the cones. You've got two different kinds of receptors in your eyes. We've got cones that give you fine detail and see color, but they take a lot of light. And then you got the rods that are your night vision, and it only sees in black and white. And those rods populate more away from the center of your eye, whereas the cones are more in the center of your eye. So if you look slightly off to the side, those more sensitive and denser area of rods, you can see better. So that reminds me. But so yeah, it'll just look black and white. Now the final thing is another deal I might have to talk Shawn into letting me put in the telescope later in the evening. Is double star. When you see some double stars, there's something about when they're so close together in the telescope. Most stars are double, by the way. Most our star is unusual in being all by itself. Most stars are in doubles or triples or quadruples and orbiting around one another. And double stars are stars that are in an orbit around one another. And when they're close together like that, and you have to use a telescope to see that it's more than one star to separate them, then all of a sudden, for some reason, the brain is able to see color. It'll detect the color. Now, the color may not be real, as I understand it. It may be a false color. But nevertheless, your brain starts to see color because of the contrast is such that it starts to pick up color. So we may try to pick out a pretty double. Got two colorful doubles I've got in mind. And then finally, there's a red carbon star, deep red star that I'd like to get on a telescope. I mean, it's nothing special about it except it's you can see the color even with your eye in a telescope. It's so deeply red. So, final thing is, and we need to get outside. These are the different kinds of telescopes you look through: the refractors, the catadioptic, the smart scopes, and reflectors. You might ask people what kind they got and have them explain to you how it works. And then the final thing is the Dark Sky Festival. Okay, there's the date, September 19 and 20. This is a map that shows the progression of light pollution since 1950. It's a very new problem that we have, and it's not just not seeing the stars. It's about human health. The American Medical Association tells us it's exposure to artificial light at night increase your risk of diabetes, depression, obesity, breast and prostate cancer, all of which are modern diseases. And it's another way of stealing habitat from wildlife. More than 1 billion birds die each year in the migration season, in part due to light pollution. So that ad wasn't intended, but I threw it in there anyway because of that map. But it's really about the festival, September 19. And of course, the festival's Arkansas Natural Sky Association, which is about light pollution. So there we are. That's done. Let's get out there and see if we can catch and see where the sun went down, and we can find the ecliptic.